Hello and welcome to my pre-recorded webinar. Today I'm going to talk about PFAS and the essentiality concept. Thanks so much for inviting me to speak at this event. My name is Ian Cousins and I'm a professor at Stockholm University in Sweden. I'm an environmental chemist by training and I've been conducting research on PFAS for over 20 years. Before I continue, I'd like to acknowledge the international collaborators and co-authors listed here who've contributed enormously to this work. So what are PFAS? Well, PFAS stands for perfluoroalkyl and polyfluoroalkyl substances. But defining what PFAS are is actually not a trivial question. The first definition of PFAS was not available until 2011. The definition is now being broadened by the OECD so that PFAS are any fluorinated substances that contain at least one aliphatic fully fluorinated carbon moiety. For example, substances are PFAS that have at least one CF2 moiety in their structure. This broad structural definition means that there are many thousands of structurally diverse PFAS in use in society. The structural diversity of PFAS means a diversity of properties and behaviors. One should therefore be careful not to overgeneralize about PFAS. They are polymers and non-polymers, neutral, anionic, cationic, and zwitterionic, solids, liquids, and gases, reactive and inert, soluble and insoluble, volatile and involatile, mobile and immobile, and bioaccumulative and non-bioaccumulative. So what are the common features of PFAS that make them so useful? The main features of perfluoroalkyl moieties are as follows. First, they have a high chemical stability due to the strength of the carbon-fluorine bond, which is often called the strongest bond in organic chemistry. Fully or perfluorinated carbon chains have even shorter and stronger CF bonds. Perfluoroalkyl chains are also simultaneously hydrophobic, that's water hating, and oleophobic or oil hating. This ability to repel liquids of a wide range of polarities is perhaps a unique property of this chemistry that is challenging to replace. PFAS are especially useful as fluorosurfactants. For example, they can lower the surface tension of water to 16 millinewtons per meter, which is half that compared to hydrocarbon surfactants. They have therefore been used in paints and inks and firefighting foams and many more applications of fluorosurfactants. They are also useful in surface protection. They have very low surface energies compared to hydrocarbon-based or silicone polymers and provide simultaneous water and oil repellency. They have therefore been used to provide non-stick cookware, durable water repellency for outdoor equipment, food contact paper, and many more applications. We all know many of the well-known uses of PFAS, such as in firefighting foams, water-repellent outdoor equipment, and non-stick cookware, but how widely are they used in society and in which applications? Juliana Gluger, a postdoctoral researcher in Martin Scheringer's group at ETH Zurich in Switzerland, recently reviewed the uses of PFAS. She identified more than 200 categories and subcategories of uses of PFAS for more than 1,400 individual substances. This figure shows some of the most used PFAS that she identified. Some of the best known uses were not the most used in terms of production volumes. Fluoropolymers tended to dominate the use volumes. The uses of fluoropolymers in the production of plastic and rubber was the #1 use. The second most important was the use of non-polymeric PFAS in the electronics industry. So this paper is already online as a preprint if you want to delve further into the details. Interestingly, a number of less well-known uses were identified, including the use of PFAS in ammunition, climbing ropes, guitar strings, artificial turf, and soil remediation. And we're still discovering more even today. Already 5 years ago, a group of international scientists, including myself, co-authored the Madrid Statement on PFAS. This statement was signed by over 200 more scientists. In this statement, it suggested that the production and use of all PFAS should be limited. It was based on the concerns regarding high persistence and lack of knowledge on the chemical structures and properties, uses, and toxicological profiles of most PFAS. So is it reasonable to assume that all PFAS are of equal concern? As we heard, they are a diverse group of substances with diverse properties. However, they all have one common feature. They are all highly persistent according to the EU REACH definition. That is, they are either non-degradable themselves or transform ultimately into stable terminal degradation products. We wrote about this problem of highly persistent chemicals in a paper published last year. We pointed out that the continual release of highly persistent chemicals results in increasing levels and increasing probabilities of known and unknown effects. And once an effect is discovered, there's little that one can do about it because the exposure is poorly reversible. We've already seen this problem occurring with PFAS. For example, the poorly reversible contamination of drinking water sources. Whereas we don't know if all PFAS are bioaccumulative, toxic or mobile, we can be sure that they are all highly persistent. This is illustrated in the radar plot in the bottom right-hand corner of the slide. We think that the high persistence of PFAS is sufficient cause for concern to manage PFAS as a chemical class, and I've written a short commentary on this. It's available as a preprint online if you would like to read it. So if we want to phase out PFAS, what are the challenges? Because of the large number of substances and broad range of uses, it's impractical to ban all uses of PFAS in one step. Some applications may serve a critical role for which alternatives currently do not exist. However, if some uses of PFAS are found to be essential, they could be eliminated without having to first find functional alternatives. We decided to examine more closely one of the famous success stories of chemicals phase-outs, the Montreal Protocol on substances that deplete the ozone layer. In this international agreement, they first introduced the concept of essential uses or essentiality, which we thought could also be applied to PFAS. So the idea is follows. To critically evaluate the idea that PFAS are essential in modern society, the essentiality of PFAS should be carefully tested against the available evidence of each of their uses. Given the thousands of PFAS on the market and their many uses, this is a formidable but necessary task. Before proceeding in this task, however, a definition of essentiality is needed, so we decided to adapt the definition from the Montreal Protocol. I'd like to point out that some of this work has been already published in the journal Environmental Science, Processes and Impact, although we're still developing it further. So in our initial work, we came up with three categories for defining if a use is essential. Category 1, or non-essential uses, are those uses that are not essential for health or safety or the functioning of society. Examples we gave in the paper were PFAS in ski waxes, dental floss, or repellent surfer shorts. Category 2, or substitutable uses, are those uses that have to be regarded as essential because they have important functions, but where alternatives exist, thus making these uses of PFAS no longer essential. Examples of the use of PFAS in firefighting foams and certain water-resistant textiles. Category 3, or essential uses, are those uses that are considered essential by society because they are necessary for health and safety or other highly important purposes for which alternatives are not yet established. Even if your use falls into Category 3, this should not be considered permanent. Innovation in the development of non-fluorinated alternatives can lead to it moving up to Category 2. I'd now like to show how the concept can be applied in 4 different case studies. Recent studies like this one by my colleagues have demonstrated that PFAS are used in cosmetics, for example in hair products, mascara, foundation, sunblocks, skin creams and lip pencils. The technical function in these products is unclear, but it could be improved spreadability and water repellency. Of course, there's concern that something that is applied to your skin could lead to human exposure. Although this is currently unproven, I can tell you that research is underway on this topic. The technical function, however, does not appear to be essential, given that when some retailers and brands discovered that their products contain PFAS, they quickly reformulated. Apparently, it's difficult to make a one-to-one substitution of PFAS with another chemical in a formulation. Instead, a completely new formulation is often needed. However, given the technical function of PFAS is non-essential, this use falls into Category 1. Fluorinated ski waxes can be bought by all of us to make us ski faster. It makes a marginal difference for an amateur cross-country skier like me, but you can't win a race without it if you're a professional. Some amateurs probably use it when they're skiing the 90-kilometer ski race in Sweden featured in this picture, as it's rather long. The waxes contain PFCAs, including PFOA, although the main ingredients are fluorinated alkanes. Functional alternatives have always been available, so they're clearly non-essential. And the International Ski Federation, also known as the FIS, decided in December 2019 to ban fluorinated waxes for the 2020 to 2021 season. There are concerns, however, that some skiers will cheat as there is a lack of availability of testing methods. Aqueous film-forming foams, or AFFFs, are a special kind of firefighting foam for extinguishing so-called Class B fuel fires. They contain PFAS, which helps to rapidly spread an aqueous film over the fire which extinguishes the flames. Unfortunately, their use has led to the irreversible contamination of groundwater used as drinking water sources in many places around the world. Historically, 3M AFFFs were mostly used. These were the so-called light water products, and they contain PFOS as well as the hexane sulfonate. Modern AFFFs are now C6 fluorotelmer based, and in recent years the manufacturers have worked to reduce the long-chain impurities in these products. Fluorine-free Class B foam, so-called 3F products, have been available since the early 2000s. I'm not an expert on firefighting performance, but I've heard that the 3F products meet the firefighting performance certifications, and as a result, many commercial airports around the world have phased out AFFFs and phased in 3F products. But the military are more reluctant. Because there's still a debate if AFFFs are needed for certain scenarios, these land in the grey zone between Category 2 and Category 3, although my own personal opinion is they're Category 2 use. The next example is an area that we've worked on in my research group. Textiles are sometimes treated with a type of polymer known as a side-chain fluorinated polymer to provide liquid repellency. As well as in rain jackets, these coatings are also used in occupational protective clothing, for example in medical gowns, military apparel, and firefighting turnout gear. This figure shows that increasing protection requirements are needed for different types of clothing. If you're going to the beach, then maybe you don't need super high protection, but if you're climbing Mount Everest or need protection against biological fluids in the case of medical workers or moisture and heat in the case of firefighters, then protection requirements are much higher. So some garments have likely been over-engineered. For example, the case of the water-resistant surfer shorts, and they are Category 1. For others, there are functional replacements that provide adequate water repellency. But for a few applications where protection is essential against fluids of a wide range of polarities, the uses are still Category 3, and innovation is needed to find suitable PFAS-free alternatives. Of course, one needs to perform many more case studies given the enormous number of uses of PFAS. This is a summary table from our paper, and we're still working on more cases in a follow-up study. In our opinion, the essential use concept can guide the phase-outs of PFAS. We believe that it makes sense to focus on Category 1 uses, that is non-essential uses, for immediate phase-out. Category 2 substitutable uses of PFAS are more challenging because one wants to avoid regrettable substitutions. The field of Chemical Alternatives Assessment, or CAA, has evolved to avoid that. Some well-known CAA methods are designed for the environment, green screen, and cradle to cradle, but there are many more methods evolving around the world. Even when PFAS are considered Category 3, that's essential uses, innovation should be encouraged to find safer alternatives. Many people around the world are now attempting to find substitutes for PFAS. So how does the process work? I've modified this picture showing the chemical substitution model from the Swedish Center for Chemical Substitution. In steps 1 and 2, one gathers information on the chemical content of products and identifies any unwanted substances. So that's been the detective work of Juliana Gluger in the paper I mentioned earlier, where she identified the more than 200 uses of PFAS. In step 3, one looks for alternatives, but one should also ask if the uses are essential. If they are non-essential or Category 1, one can phase out the PFAS and stop here. If they have an essential function, then one continues to step 4. In step 4, one evaluates if there are alternatives available. If there are none, one proceeds to step 5 and develops new alternatives. If there are alternatives that can fulfill the function, then one must assess the alternatives against existing products to ensure that one is not causing problem shifting or regrettable substitution. For example, one may reduce the chemical impacts but increase the climate impacts. Here there are many tools from the field of chemical alternatives assessment that can be applied. An example of a CAA tool is life cycle impact assessment. And we recently developed and applied a life cycle impact assessment framework for PFAS. But this is just one part of the CAA process, of course. I believe we have reason for optimism and that a systemic change is underway. PFAS are under global pressure. So let's look at the drivers and inhibitors of change. I modified this slide from the POP3 project, which is a Swedish project where industry have received government startup funding to phase out PFAS from a number of use cases. Many companies are actually pushing to phase out PFAS in their products and are innovating along the value chain to ensure that. So phasing out PFAS and other hazardous chemicals is not anti-business, it's good for business. So this is the push and the yellow arrows on the figure below. Then we have the pull from NGOs, consumers and authorities. In my opinion, the pull is greatest from consumers and NGOs because actually chemical regulation can be a frustratingly slow process. And then finally, as well as the push from certain parts of industry, we have the push back from other parts of industry, especially the fluorochemical industry, who have a vested interest in protecting their chemicals and products. I'd like to finish with an optimistic message. There is a reason for optimism given the speed at which things are changing in certain use cases. These successes include the banning of PFAS in paper and board used in food contact materials in Denmark, the banning of fluorinated ski waxes in international competition, the transition to Class B fluorine-free foams around the world, the phasing out of PFAS in cosmetics by multiple retailers, and the introduction of a wide range of fluorine-free, durable, water-repellent outdoor equipment in the marketplace. But there are greater than 200 uses, of course, so the work is far from done. An exciting development in the European Union is the preparation of a broad restriction proposal for PFAS under the EU REACH regulation. This is being prepared by the more progressive countries in the EU when it comes to chemicals management, namely Denmark, Germany, the Netherlands, Norway and Sweden. It's unclear which PFAS will be included in the proposal, but the ambition is to be as broad as possible and include as many PFAS and uses of PFAS as possible. Interestingly, the concept of essentiality will probably form the basis for exemptions to the phase-out. Interested parties were invited to send in evidence and information on the uses of PFAS by the 31st of July this year. The paper that I mentioned earlier by Juliana Gluger was a key piece of evidence on the uses of PFAS. We purposely published it as a preprint so that the evidence would be available before the regulatory deadline. So a few acknowledgements. All co-authors are members of this new organization that we created, the so-called Global PFAS Science Panel, and our activities have been funded by the Tides Foundation. And a couple of my co-authors would like to include disclaimers. So thank you for your attention and I look forward to the discussion. I realize I've got a couple of minutes left, so I thought that I'd quickly bring up a few points that might be interesting to discuss. These are thoughts that have crossed my mind in recent times. So first of all, what should the scope of the essentiality concept be? Should it be applied to all uses of PFAS? Do we agree that all PFAS are equally problematic? Should the concept be applied beyond the uses of PFAS to other chemicals of concern, and if so, which ones? Could it be applied, for example, to uses of microplastics? Some scientists have already proposed this. Then once we've agreed that we want to apply this concept, what about its practical application? Are the criteria we invented too vague, and do they need modification? How can they be improved? How do we determine what is essential for society, for example? And who should be given the job of deciding if a use is essential or not? Should it be the manufacturers, or the regulators, or someone else? Also, I noticed the concept sometimes gets blurred. Some industrial scientists are happy to discuss essential chemicals and products. I think that is concerning because no chemical should ever be considered essential and irreplaceable. It's important to remember that the concept should be applied to the uses. One problem we have is that we know little about the uses, and we have to spend a lot of time doing detective work to determine what PFAS are used in. Should we really be wasting resources on this when industry know very well where these chemicals are used? Scientists often have to reverse engineer products by conducting chemical analysis to determine what's in them. Chemical alternative assessment has been developed enormously in recent years. As somewhat of an outsider, I found these analyses extremely complex, with an enormous number of input variables and potential outcomes. And I think the outcome can depend on who's conducting them. We want to avoid paralysis by analysis and decision making, but how can we simplify the analysis while still protecting against regrettable substitutions? Who should perform these chemical alternative assessments and how? So these are just a few of my thoughts for the discussion, which I'm looking forward to enormously. Thank you very much.